This is section 8, implicit differentiation, example 4. So for example 4, we're actually going to take what we know already and apply it to, we're kind of extending it beyond what we would normally think about when we're talking about just taking a derivative. And that is finding horizontal and vertical tangent lines. Now we know that to find the slope of a tangent line means that we take the derivative. And so that's what we're going to do. So the first thing I want to do with example 4 is take the derivative. Then we'll figure out where it's horizontal and vertical. So we're taking the derivative implicitly. So we do the power rule. Right? So we're taking 2, multiplying it. So we have 50 x dx dx plus 32y dy dx plus 200 dx dx minus 160 dy dx equals 0, right? Because remember, the derivative of 400 is just 0, so we don't have to include it. Now don't forget, when you have dx dx, it cancels to equal 1, so we don't have to worry about that, and our job is to solve for dy dx. To solve for dy dx, I'm going to take 50x and 200 and move it to the other side. So I will be left with 32y dy dx minus 160 dy dx on the left, and that will equal negative 50x minus 200. Now, dy dx is in both of the terms on the left side, so I can pull it out. We get dy dx times 32y minus 160 equal to negative 50x minus 200. And if I want to get dy dx by itself, I divide. So dy dx ends up equaling negative 50x minus 200 over 32y minus 160. Now, when we're solving this problem, what I have just found is the derivative. I haven't answered the question. It's asking for the points where the curve has horizontal and vertical tangents. So to figure this out, the first thing I have to do is define what that means. Well, if I have a horizontal line, I know it looks like this, which means that the derivative has to equal 0, because the slope has to equal 0. If it's vertical, then I've got a line like this, right? And that has an undefined slope, right? Because remember, it has a rise but no run, and you're not allowed to divide by 0. So that means that dy dx does not exist. Now, when we're talking about rational functions, we have to remember, using our vast knowledge of algebra, that when a rational function is 0, the numerator is 0, and when it's undefined, the denominator is 0. So let's start by finding our vertical tangent lines. So, does not exist. And we know it does not exist when, like I said, the derivative is undefined, and it's undefined when the denominator equals 0. So I'm taking the denominator, which is 32y minus 160, and setting it equal to 0. I'm then going to solve for y, which is very simple, right? It's linear. So y equals 5. Now, that means that that is the y value where it would occur. It's asking for the points. For a point, you need an x and a y value. To get the x value, we're actually going to take this y equals 5 and plug it back into the original equation. Okay, every time we see a y, and then we'll solve for x. So it does take a little bit of time. So let's go ahead and do that. When I plug it in, we get 25x squared, no change, plus 16 times 5 squared, which is 400, plus 200x. Then we're plugging y in again for 160 times y, so 160 times 5 is negative 800, and then plus 400 equals 0. So now I'm going to simplify the numbers. 400 plus 400 minus 800 all cancel out, and we're left with 25x squared plus 200x. Well, 25x squared and 200x both have factors that we can pull out. They both have x and they both have 25. So I'm just going to go ahead and do that. So that means we have 25x times x minus plus 8. equal to 0. Remember, when you factor and you get the answer, it's just setting your factors equal to 0 and solving, right, just like we've done in the past. So we get 0 and negative 8. Now again, this isn't the point. We don't have actual points. We have x values, we have y values, now we have to put them together. So the answers end up being 0, 5, and negative 8, 5. Those are the coordinate points. Okay, so that's half of our answer. Because that's only finding where it has vertical tangent lines. Now we have to find out where it has a horizontal tangent line. So let's do that. So horizontal, which means that it equals 0, right? That's what we're going to find now. So that's what we found. And to do that, we have to set our numerator equal to 0. So we end up with negative 50x minus 200 equals 0, which means that negative 50x equals positive 200, and x equals negative 4. So that means with the points that we end up with, the x values for both of them are going to be negative 4. We just need to find the corresponding y values. To do that, we're going to take this negative 4 and plug it into the initial equation, just like we did with the vertical tangent, the 5, and see what we get. So we get, let's see, 25 times negative 4 squared is 400. Then we have plus 16y squared. When we plug in negative 4 to 200, we get negative 800 minus 160y plus 400 equals 0. And this is what we're solving for y. Well, all of the numbers, again, conveniently, very conveniently cancel out. That it will not always happen. It happened to happen for both parts on this problem. Don't get used to that, right? Then you just factor like normal. It's still a factoring problem. It should be very nice to look at. Now, both of these terms have 16, and they both have y. So we take 16y out. We end up with y minus 10, which means that y equals 0 and 10. And the points are negative 4, 0, and negative 4, 10. So we have 4 points to answer this question. They are 0, 5, negative 8, 5, and negative 4, 0, and negative 4, 10.